Section 3.7 deals with implicit differentiation. We will be also talking about higher order derivatives and rational powers of a differentiable function. In order to understand implicit differentiation, first we have to review what the words implicit and explicit actually mean. Implicit or implied is something that's not immediately obvious, but that can be figured out logically. Explicit essentially means something that's very obviously stated. Here we have a table of 6 different functions. On the left-hand side, we have functions in their implicit form, and on the right-hand side, we have functions in their explicit form. Now notice something interesting. On the right-hand side, we always have y equals something, for all 3 of them. It's explicitly stating that y is equal to x and some constants. However, on the left-hand side, things aren't so obvious. We would have to solve for either y or x in order for our function to be in its explicit form. Let's say we wanted to take the derivative of the implicit functions on the left-hand side. There's actually 2 routes we could go with. If we wanted to take the derivative for each of these functions with respect to y, we could just simply solve for y. But let's see what happens when we do that. Let's use the implicit function x squared plus y squared is equal to 16. You may or may not have noticed that this is the typical form of the equation for a circle. Now, if we wanted to take a derivative of this function, let's say the derivative of y with respect to x, we could do 2 different things. The first thing we could do is simply solve for y. And let's go ahead and do that. Now we have our function in its explicit form. It straight up just says that y is equal to plus or minus 16 minus x squared. Now, just taking a look at this, you might have guessed that this would be rather hard to differentiate. So is there another way we could take the derivative of this function right here without having to solve for y and without having to deal with this mess? And that's where implicit differentiation comes in handy. What it essentially is what implicit differentiation essentially means is that we can take the derivative of these guys over here on the left without having to go through the hassle of solving for one of the variables first. To do this, it takes 4 different steps. First, we have to differentiate both sides of the equation with respect to x. Then we have to collect the terms with dy dx on one side of the equation, factor out dy dx, and then solve for dy dx. And we could do that for a very similar problem to what we just saw, where we had x squared plus y squared equals 16. Here we just have x squared plus y squared is equal to r squared. We're going to find the derivative of y with respect to x without having to solve for y first. And this is how it's done. First, we need to set up our Leibniz notation, which is going to look something like this. We have d dx x squared plus d dx of y squared, which is equal to d dx of r squared. Now, the first rule that we can apply, first derivative rule, is the derivative of a constant function rule, where we know that if we take the derivative of a constant, it's just equal to 0. If we have an equation for a circle, like we do right here, we know that r squared stands for radius squared, and the radius is always going to be a constant, which means it can go away. Then we can differentiate further. We can apply the power rule to both x and y, which will give us this. Now notice something interesting here. When we have d dx of x squared, we just do what we always do. We pull the 2 down in front of the x and get 2x. However, when we do d dx of y squared, we have to remember this crucial extra little step. We also do 2y, where we pull the 2 out in front of the y and it becomes the coefficient. But we have this little dy dx tacked on at the end, and that's very important. That's because you took the derivative with respect to x of y squared and not x squared. So basically you have to account for that by saying that you have dy dx right here. The next step is just some basic algebra. We're going to put the 2x over to one side, and finally divide out the 2y on the left-hand side to get the following. We have dy dx is equal to negative x over 2. Now remember, this right here is the derivative function, the derivative of this guy over here. We didn't have to solve for y before doing it. We just had to implicitly differentiate, which makes our life a lot easier. Now, an extra step that is optional but highly recommended is that after getting to this point, you change from Leibniz notation to the notation using primes, which will just look like this. Y prime is equal to negative x over y. Why did I do that? Well, this looks slightly less complicated than this. Now, again, Leibniz notation is very useful when you are doing some algebraic manipulations to your derivative function, which we were doing right here. However, as soon as you're done with that, you can just say y prime is equal to negative x over y, and that'll polish up and make it look a lot cleaner. Let's take a look at some more complicated examples of implicit differentiation. Actually, this one's not too bad, but it's just kind of what we were talking about earlier. We have y squared is equal to x, and we want to find a derivative of y. However, we don't want to have to solve for y beforehand because then we have a square root, which gets kind of messy. So instead, we just apply our derivative rules right away, which gives us dy dx is equal to 1 over 2y right here, just by doing our derivatives as we did before in the previous example. Now again, they don't have it written here like this, but you can rewrite this as y prime is equal to 1 over 2y, if that's easier. And if we were to graph this, it would look like this strange sideways parabola. Now, of course, this is technically not a function because it doesn't pass the vertical line test, but it's still kind of interesting to see. We have another example over here where we have x squared plus y squared is equal to 25, and this is going to be following the same exact process we did before. In fact, the answer is negative x over y, and if we go back over here, we can see that we had the same exact answer. dy dx equals negative x over y. And it's the same right over here. The only thing that is different is that here we have a 25 instead of r squared. But that's a very interesting detail too, because as you recall, anytime we have an equation in the form of x squared plus y squared equals something, that's the equation of a circle, as we can see on the bottom here. So you can tell just by looking at the circle that no matter how big or how small it gets, as long as it's a circle, the derivatives are going to, what the tangent lines look like as you follow the circumference of the circle are going to look just about the same, no matter if the radius is 10 or 100 or however big or small. We've touched on this briefly before, but we can talk a little bit about higher order derivatives. Now again, we see this prime notation, this apostrophe. If you count those, that'll tell you what order derivative it is. So again, at the top here we have the original function, and there are 0 apostrophes, 0 primes, so that's got to be our original function. Here we have 1 apostrophe, so that's our first derivative. Now, if our original function was position, distance, or height, then our first derivative is going to be velocity. Our second derivative is going to be acceleration. Our third derivative is going to be jerk, like we talked about in our previous section. Jerk helps determine what bodily harm would come if you're in a car and you get into an accident or you have to slam on the brake. The faster you slow down or come to a complete stop, the more dangerous the crash, essentially. But here we have the fourth derivative, and when we're talking about position, distance or height as our original function, there's not a whole lot of utility to a fourth derivative. Once you get past a certain point in taking these derivatives, they're no longer really that useful. But you can also see that if it's such a high order, then we don't even use the apostrophes anymore. We just put number 4 or in Roman numerals like that. But we can quickly look at an example here of taking a higher order derivative. So we have this function, and this is using implicit differentiation again. Except right here, they didn't even use Leibniz notation. They just went straight to y prime. So we don't have to go into too much detail about this. But this is using implicit differentiation to get our first derivative function. And then if you take the derivative again, you can get your second derivative, which looks a little something like this. So for example, if this original function here was some function of position or distance or height, this one right here would give you the velocity at any given moment, and this one right here would give you the acceleration. Finally, to wrap up this section, we're going to talk about the power rule for rational powers of x. So this rule states that if n is any rational number, then the derivative of x raised to the n is equal to n times x raised to the n minus 1, as we can see over here in the bottom. Now, you might be asking yourself, well, isn't this just the same exact thing as the power rule that we already talked about? The answer is yes. The only difference is that there's a small caveat here. If n is less than 1, then the derivative does not exist at x equals 0. So that means if the exponent up here has a value of less than 1, then at x equals 0 there is no derivative, it's undefined. And we can take a look at what this looks like graphically. Now up here in the corner you can see we have y equals x raised to the 0.3. And the power is less than 1, which gives us this strange looking kind of sideways half parabola. And if I take the derivative of this function and I enter it in like this, we have our derivative function in black. Now notice what happens. Notice what happens as I approach 0, x equals 0. Well, it looks like our derivative function here, which is black, shoots up to infinity, which means that at that point it's undefined. And that actually makes perfect sense. If I were to draw the tangent line here at 0, it would point straight upwards, which means that at that point the derivative is undefined. If we take a look at our tangent line plotter, we can see the same thing. On top we have x raised to the 0.3, on the bottom we have the derivative function, and as I go closer and closer to 0, it shoots up into the sky. And our derivative is undefined. See, it doesn't even want to show it, going straight up. And that about does it for section 3.7, dealing with implicit differentiation. This method of taking derivatives will become very useful later on if you decide to study about differential equations.